My name is Matthew Cowell, and I will be sharing our CVPR 2024 highlight paper on Visual Concept Connectomes. Concept-based interpretability aims to uncover human interpretable concepts and the intermediate representations of a model. These approaches first discover concepts and then quantify their importance to the model output. However, none of these approaches tackle the question of how these concepts arise in the model in the first place. To this end, the goal of this paper is to design a methodology that quantitatively measures the contribution between any two concepts at different layers of a deep network. For inspiration, we look at the brain and the idea of a connectome, which is a complete map of neural connections in the brain. Alternatively, for a deep network, we propose the Visual Concept Connectome, a comprehensive description of a DNN via human interpretable concepts and their interrelationships. Constructing a VCC takes three things as input: a model, a selection of layers, and a set of images. It involves three steps. First, top-down feature segmentation is used to produce the base units that will make up concepts. Passing an image through a model, we then cluster the representation using SLIC to obtain connected segments. Doing this recursively over all image segments and layers produces a data set of image segments for each layer. Second, we perform layer-wise concept discovery. Given a set of images at different layers j and I, we perform k-means clustering to obtain per-layer concept centroids. Finally, we compute the contribution of earlier concept Ci to deeper concept Cj. To do this, we define a vector for the earlier layer concept and see how well it aligns with a vector for the positive contribution to the later layer concept. To obtain the final VCC, we compute edge values for all adjacent concepts and prune edges through statistical testing of many sets of random images. Let's look at some qualitative examples of VCCs. Here we show a three-layer VCC for the GoogleNet model targeting the class J, where darker lines denote higher edge strength. Early layers show concepts like bird necks, beaks, and edges. Looking deeper in the model, we see the Inception 5B bird concept composed from head, branch, and body concepts, while background concepts are composed of other background concepts, leaves, and branches. At the final layer, we see both foreground and background concepts highly contribute to the class logic, while a closer introspection reveals the model encoding separately the concepts of blue jay and other J types, an example of emergent unsupervised subclass separation. We now show a VCC for the VGG16 model targeting the class tow truck for all convolutional layers of the model. Shallow layers on the bottom and deeper layers are on the top. At shallow layers, we see basic concept composition such as edges and brown forming oriented brown edges. At mid layers, wheels and asphalt are composed of the concepts wheels and road, while at deep layers, we see again that both foreground and background concepts highly contribute to the class logic. VCCs also provide the ability to quantitatively analyze concepts and connection distributions across models. We use common metrics for tree-like structures: branching factor, number of concepts, average edge weight, and edge variance. We first performed analysis of architectures by comparing CNNs and transformers. We see that CNNs reduce their branching factor as they go through the model, but transformers have a higher edge variance of edge weights at the final layer, suggesting transformers are more compositional at the late layers than CNNs. We also compare training objectives for the same model, specifically self-supervised and adversarial robust trained models. We observe that self-supervised and robust models contain a smaller branching factor and fewer concepts at early layers, likely due to training protocols that perturb color and texture information. Finally, we provide application of the VCC to model debugging, in particular determining the internal conceptual errors that a model is making that lead to mistaken predictions. Shown in the middle is an image of a tricycle predicted as a rickshaw decomposed via top-down feature segmentation. By looking at whether the tricycle or rickshaw VCC concepts are closer in feature space, we see that the model correctly encodes the handlebars and wheel as tricycle concepts starting as early as layer 2. However, the model falsely recognizes the hood of the bike as a rickshaw concept, again starting in layer 2 and remaining until the final layers. Thus, VCC offers a novel and interpretable approach to understanding mistakes that are made by a DNN. In summary, we present the Visual Concept Connectome. We use the VCC for qualitative and quantitative analyses of various models and tasks, And finally, applied VCCs for the application of hierarchical model debugging. Please visit our project page and paper for code and more results, and we hope to see you at our poster at CVPR this year.